Hello, everybody. Welcome to our live for today. Today, unless anybody has any questions, always feel free to drop them in the chat. We're just going to pick up where we left off yesterday here. Let me open this. So, yesterday, what we did, we talked about something seemingly crazy, I'll say, or at least in terms of the amount of work involved. So, let me share that real quick. All right, there we go. Cool. Is that coming through? Does everybody see that? Okay. Yeah. So that's good. So yes. So what did we talk about yesterday? And actually, let me talk about before that. So before that, so 2 days ago, we were talking about the idea about how when we have a Riemann sum like this, we could approximate, keyword being approximate, the area under the curve of a function with n different rectangles, basically. And we call those partitions, the way we break up the interval. And we talked about a couple of different methods, use like for how to select the sample point, basically the right Riemann sum, left Riemann sum, midpoint. I won't rehash all of that. And we walked through some specific examples with some specific numbers, and we got our approximations right. We got the right Riemann approximation, the right, or sorry, the right, the left Riemann approximation, the midpoint approximation. We got all these approximations. Yesterday, what we talked about is how to not just get the approximation, but get the exact value. And the way we did that, remember, is basically we started off with the Riemann sum and we just let the number of rectangles go up to infinity, right? If you just keep increasing the rectangles forever, whatever this number approaches when you actually add up all those areas, that is the approximate area under the curve. And you can see it's like it looks like a much better, it's still rectangles to be clear, unless you zoom in a lot further. But if you just keep cranking up the number of rectangles, you can see that like the overshoot and undershoot goes down by a lot, right? And we get to the point where we're getting almost the exact area under the curve. So hopefully that all makes sense conceptually. The way we do that is very complex. Basically, we still use, actually, the idea is simple, it's just doing it is hard. We still use the same Riemann sum formula, right? This is the formula that we've been using, and we use the right Riemann sum to choose the x value because that's easier. But this is the same formula we've been using, like 2 days ago, for example, the day before yesterday, to calculate the Riemann sum approximation, right? With an actual value for n. The difficulty here is that, or I guess how should I word it? The difficulty is that now how are we going to do this with infinity? We can't literally add up an infinite number of numbers. That's true, we can't. But what we can do in calculus is we can take the limit as n goes to infinity. So in other words, we try to solve this whole thing and get a function in terms of n, where n is the number of rectangles. And then once we do that, like once we get rid of the summations and everything, we basically we basically let n go to infinity, let n keep growing forever. That simulates what we did over here, right? Where we basically start with a smaller n and we just keep cranking n up. We just keep cranking. We use the same formula every time, but we're just cranking up the number of rectangles. And you can see it's more and more closely approximating the exact area under the curve. So that's that. Now, obviously, the way we did it is pretty complex, right? It's like 15 lines for the derivation. But once we did that, we got 12 at the end, which was pretty close to what all our approximations were, like 11.25, like 12.2625. Like it was between those. So this is the exact area that we get. So this is how you find, and actually I'm going to use a new word today that we kind of haven't used before. So what I'll say, let me actually grab the formula here. So if we grab this, I'm going to pull this over to today. This crazy formula that we used, or that we used yesterday. Let me create a new one for today. Just a second. So this crazy formula that we used yesterday, that is something that is called the integral. So instead of just thinking about it as the area under the curve, which it is, by the way, we give a new symbol to it. The symbol is the integral from a to b of the function f of x, and then we do dx. This is the integral symbol, and this is called the definite integral. We'll talk about later something called the indefinite integral. That's a little bit more complex. But anyway, this is what we just used, the definite integral. It's the reason it's definite, by the way, is because we are sure about what the bounds are. Like we have bounds. So visually, what this represents, again, it's this thing, this new symbol we're adding is the area under this curve f of x between a and between b. So that's what we're doing here. So there you go. Hopefully that makes sense. Now, when we're looking at this, I guess I'll say, what should we do here exactly? So basically, this is the idea. And now the next question is like, how do we have to do the all the work we did last time every single time? Because obviously it was very painful to do that. We could do it, but it's hard. It's hard. This is like I said. I think this is. I would say that this is the hardest topic in AB in calculus AB. In calculus BC, there's a couple topics that are slightly harder, but this gives them a run for their money. I'd say in terms of the difficulty of this concept. Like this is another word. Like what this really is. Another way you can think about it is this is the limit definition of the integral. If you want to think of it like that, we talked probably a lot earlier in the year. So limit definition of the integral. We talked about the limit definition of the derivative much earlier in the year. This is the limit definition of the integral. So hopefully that makes sense. Now, the next question is what do we actually do with that, or what do we actually like? How can we bypass that work? And this is what we're going to talk about today. So we're going to talk about the same actual setup, and hopefully this is clear for what we did yesterday. So just as a refresher, to be clear, I'm actually going to grab the same problem, the same exact problem. Yeah. So this was the question. Find the exact area. Again, we're no longer approximating. We're talking about exact areas, but it was find the exact area under the curve between x equals 1, or sorry, x equals -1 and x equals 2. So what that is here, that's like using this new terminology that we're talking about, using this new symbol. The a is -1, the b is 2, and the f of x is that. So what we're really talking about, you can think of in this problem, and this is what you'll start to see as you come across this in class, but -1, 2, and the function itself, 5 minus x squared, and then a dx. So I kind of think of like this integral symbol. We'll talk about that in a second. And then this dx, think of them as a box where you put your function in, and that function is the thing you want to integrate. And by the way, before we go on with that, let me just mention this too, just to talk about a little bit of the terminology here. Hopefully, you can tell by looking at this that it's the same symbols, right? Roughly. So, like the thing on the left here, the reason the symbols are the way they are, we're really just trying to do the same symbols as this limit, because it is a limit at the end of the day. An integral is, but we're trying to do it with like continuous variables. So like the delta x, the change in x, that becomes dx, which is, if you've seen that before in calculus, that's called a differential. It's basically the idea is that it's an infinitely small change. Delta x is like a change in x that's finite. This one is like an infinitely small change in x, which again, it's kind of just a conceptual, kind of like just a concept difference, really. Like you can't actually, like the differential is not really real, I would argue, in my opinion. It's kind of a construct, but that's kind of the idea. It's like if you take this to the extreme, because right, as n goes to infinity, as the number of rectangles goes up, so like going back to this visual, as the number of if I like double the number of rectangles, I have the width of each rectangle, which is delta x. That's why that happens, right? So as n goes to infinity, delta x is going to shrink to 0. So it's like that's what we mean by the dx. So hopefully that's clear. And then here, hopefully this is clear that this goes together. So instead of choosing the function at a sample point, we choose the function at a specific point. The meaning is, so like, remember, if the whole point of a sample point is you can actually choose any x value you want, or like any x value you want within a partition, and then plug it into the function, right? That's according to the official definition of the integral, you can do that. However, as n goes up, it's like, you see how you're getting it for, like, you again, like I can zoom in here and say you can still pick any value, or if I can grab this, right, hold on, you can still pick any value you want between there, but you see how you're kind of getting forced to one value. As n goes to infinity, the width of each shrinks, so it's like it's forcing you down to one exact x value. That's why we don't have to do this star. That's why we don't have to do the star on the left, because because it's not a sample point anymore. It's not like we're sampling an x value. It's like there's only one x value that we can pick at all, because we're getting forced to pick one specific x value. And then this last part, this part, or I guess more like this part, that is essentially that symbol. So this is the Greek letter sigma, capital sigma, and it represents summation, adding a bunch of stuff. which we talked about before. This is like the continuous version where you add up an infinite number of rectangles rather than just like a finite number. So this is like, you can kind of see it kind of even looks like an elongated S. It's called a summa, like SUMMA. I think that's Latin. The person who discovered calculus, or one of the people who discovered calculus, uh, basically came up with this in his notebook. But the idea is it was kind of supposed to be like this is kind of like the sigma. This is like the Greek letter S. This is supposed to also kind of be an S, but like obviously a different symbol. But it's like, again, it's just symbols. That the bottom line is the left side is just symbols to represent the thing on the right. But hopefully you can see like they kind of loosely match up the same ideas. So that's just like a discussion about the notation. So what I want to do today, and this should be less painful than yesterday, but I basically want to do the exact same problem we did yesterday, but with the less painful method. So here, and you'll see how much less painful, right? So just as a refresher, we did the same exact problem yesterday. We tried to find not an approximation, but the exact area under the curve. And the way we did that was basically we, I guess how should I word it? We basically had to solve this entire limit, right? And this is a limit of a summation, which is extremely complex. Again, just walking through the work here, we did all this crazy work, and I was trying to like draw on the right hand side just so we could visualize like what's actually going on and why we can do all these tricks. But basically, we did a bunch of tricks manipulating the summation formulas, and then at the very end, we like used we talked about like kind of the Gauss, the trick that Gauss figured out when he was a kid, and then the generalized form of that equation. So we basically use special knowledge of what summations equal to solve those in terms of n, and then we after that we simplified the whole thing, and then we got this, and then we or got the last thing, I guess, and then we took the limit as n goes to went to infinity, and long story short, we got 12, and that's the exact area under the curve. So what I want to show is we're going to get the answer is 12 again, but it's going to be like one tenth of the work. So that's my goal. 1/10 of the work, 1/10 of the complexity. So how do we do it? It's actually kind of simple once you know how it works. So here's the rule, and I'll just show this over here. So whenever you have a formula, so like I'm just going to say, and I'm just going to compare this to what's going on the right hand side here. So actually, I'll pull it down like this. Whenever you have an integral like this that you're trying to solve, so whenever you have, let me copy this. Whenever you have an integral like this that you're trying to solve, you basically have a equals -1, b equals 2, and f of x. So we're just getting clear on what all of these are. So that's just the setup. But how do you actually do this? Well, I'll just write some symbols that might not make sense, and then I'll explain what they mean. So I'm going to write capital F of x rather than lowercase f of x, and then this kind of slanted line, AB. First, it's probably easiest to talk about the slanted line. All the slanted line means is plug b in for x, then afterwards plug a in for x to the function, whatever it is, and then subtract it. So basically, whenever you see this formula, it literally means capital F of b minus capital F of a. So that's kind of the easy part. That's just normal algebra. The hard part is finding capital F from lowercase f. So what is that? Basically, there's two ways of thinking about it that are equally valid. So what we call capital F, we say that capital F of x is the antiderivative of lowercase f of x. That's one thing that we could say. And then the second thing that we say is that you could also word it as lowercase f of x is the regular derivative of capital F of x. So two different ways of describing the same concept. So in other words, just to be clear, what is capital F? It's whatever function, when you take the derivative of it, equals this. That's what it is. So it's kind of like if you're starting with lowercase f and you want to get to capital F, you kind of have to undo the derivative or take the derivative backwards. That's what we mean by the antiderivative. So what I'm talking about now, by the way, is called the second fundamental theorem of calculus, or in some classes, the first fundamental theorem. But this is how you solve integrals. And again, I know this seems pretty abstract, but so let's talk about an example. So think about it. We can break these apart. So instead of 5 minus x squared, think of them individually. Let's just start with 5. What function do you know who has a derivative that has a derivative of 5? That's the question. We're trying to find the antiderivative of that. So we're trying to work backwards. Think about it. Feel free to write any answers in the chat if you have any ideas. The answer, if you think about it, is 5 times x, right? Because if you have 5 times x and you take the derivative of that, that will equal 5. So you can word it two ways. You can say 5 is the derivative of 5x, or you can say that 5x is the antiderivative of 5. Both of them are valid. So that's good. And then what about x squared? What function do you think, what would you have to take the derivative of to get an x squared? Think about it like that. If you think about it, hopefully it's clear that if you have x cubed and you take the derivative of that by the power rule, right, it's 3x squared. But we don't want 3x squared. We want just x squared. We don't want the 3 out front. So you can just do that, x cubed, but divide by 3. So in other words, x cubed over 3. And then see if that makes sense. X cubed over 3. If you take the derivative of that, or 1/3 times x cubed, actually, let me write it that way, minus 1/3, the 1/3 times x cubed. If you take, hopefully it's clear, if you take the derivative of this, you bring the 3 down, 3's cancel, and then you subtract 1 from the power, you just get x squared. So yeah, actually, negative x squared is the derivative of negative 1/3 x cubed. So this whole thing is the antiderivative. This would be like capital F in this example. And then we just evaluate it between A and B. Now, how do we evaluate it between A and B? Remember, all this symbol means is this is your function, this is your antiderivative. That's the hard part, figuring that out. That's the calculus part that you have to figure out. And this is the good news, by the way. Well, actually, let me back up a little bit. I'll come back to this in a second. Well, let's just solve this first, just to prove that we get the same result, and then I'll talk about this a little bit more. So how do we do this? Remember, instead of like B, so like think about what B is 2 here. So B is 2, A is -1, right? And then how do we do that? Well, first, we just plug in f of 2. What's f of 2? Well, it's 5 times 2. So 5 times 2, right? Minus 1/3 times 2 cubed, right? So that's like f of b, what we've written so far. We just take b, 2, and plug it into the function, like x equals b. Wherever you see x, plug in b. And then you subtract, and then you do the same thing, but f of a. So it'll be 5 times -1 minus 1/3 times, I'm just going to make a little bit of room here. Let me pull this over. -1, so -1 cubed. So there you go. And if you see here, these are just numbers. So you can solve this. Let's actually solve it and see what happens. So what's 5 times 2? That's 10. Minus what's 2 cubed is 8. So minus 8/3, which is really, if you think about it, 2 2/3, but we'll just leave it like that. Minus what is 5 times -1? -5. And then -1 cubed is -1. So -1/3 times -1. Hopefully that's clear. Positive 1/3. So there we go. And then as we're thinking through this, let's clarify. So what would this be if I simplify all this stuff? So what would I get? I get 10 minus 8/3. And then what I would do is I would distribute. You can simplify obviously however you want. I'll just distribute the negatives. So plus 5 minus 1/3. So think about it. This is actually going to be 15. We add 10 plus 5, and then minus 8/3 minus 3/3 minus 9/3. What's 9/3? That's 3. Answer is 12. So remember all that crazy work we did before? So all that crazy amount of work, like literally 15, 20 lines of nonstop pain to get to that number 12, that all gets replaced with this new technique, which is only like 3 lines or 4, depending on how you count. So much less painful. You don't have to think about the limit. You don't have to think about any limits as n goes to infinity. You don't have to think about any summations. You don't have to do any of that stuff. The trade-off, this theorem encapsulates all that logic we talked about before. Again, I haven't explained why this theorem is true, but hopefully this gives you a little confidence that it is true. But the only trade-off, the only hard part, so to speak, is that given the function they give you, you have to be able to find the antiderivative. That's the only hard part. It's not that hard a lot of the times once you know how to think about it. That's the good news. So I'll wrap up here, or I'll just mention this before we wrap for today. Remember when you're taking, like, basically, there earlier in the year at this point, you should have all been spending a certain amount of time taking derivatives, right? You basically, they give you a function, you find the derivative, etc. So you've already done that a lot probably. And now here, I guess, how does this change things? Basically, the idea is that in order to take the derivative, you basically remembered a lot of rules, specifically, like, depending on how you count, 22 rules, let's say, that you remembered to actually take the derivative quickly and efficiently, as opposed to using the limit definition of the derivative. That's actually the exact analogy for what's going on here, by the way. If you remember back earlier in the year when you did the limit definition of the derivative, that was painful. And then you learned the derivative rules, which, again, it took some getting used to. But once you got the rules, it was way simpler and way faster than using the limit definition of the derivative. This is what we just did for the integral. What we did yesterday with those crazy limits and those summations, that was the limit definition of the integral that we used. We solved the problem with the limit definition of the integral, which was way more painful than the limit definition of the derivative, right? Now, what we're talking about here is essentially integral rules. So just like you had derivative rules, you had integral rules. And you basically, there's the same amount of rules too. There's like 22 integral rules, depending, again, around there, depending on how you count. It varies a little bit. So you might think, that's the hard part. You might think, oh, okay, I see. So if I learn 22 more rules, then I'll be able to do these. Yes, but it gets a little better. Those integral rules are not just random integral rules. Because remember, the integral, or the antiderivative, however you want to call it, is the opposite of the derivative, loosely speaking. And we'll talk about this. So every rule that you learn for derivatives is the opposite of a rule, or sorry, every rule that you learn for integrals is the opposite of one that you already know for derivatives. That's the good news. So you already know the rules, I guess, is the point. They're already in your head right now, or at least they should be. You just need to learn how to think about the rules you already know backwards. And that's what we're going to be talking about in a lot of the future lives. So hopefully that idea makes sense. But that's the one hard part, right? So this part, like, after you get to here, that's easy, right? That's just, you just plug in, evaluate. Again, there's algebra involved. You can definitely make mistakes. You got to be careful. But it's nothing crazy conceptually, I would say. The hard part is just getting from here to here, finding the antiderivative with the integral rules, or the antiderivative rules. So that's what we're going to spend most of our time talking about next time. And then again, I'll just show, the good news is, again, it gets better. It's not like you have to learn 20 new rules like you did with derivatives. You already know the rules. You just got to learn how to think about them backwards. That's the good news. So all the rules that we learn are connected. They're literally just the opposite version of the derivative rules. And that's what we'll talk about next time. So hope that helps. Hope that makes sense. Like I said, feel free to drop any questions or comments in the Skool community, and I'll be sure to answer them. I'll create a video kind of walkthrough of all of them. But yeah, other than that, hope that helps with everything. If you have any questions, just let me know. Otherwise, have a great weekend, and we will start back up on Monday. See everybody later.